Well, I'll come you back. I welcome you back. And in the previous video, I told you how to draw a boiling point composition diagram from a vapor pressure composition diagram. Yes. Now, for this case, I told you that we are going to be looking at fractional distillation of a liquid mixture that deviates positively from Raoult's law. Now, after having plotted the boiling point composition diagram, or after having drawn it from the vapor pressure composition diagram, you can be told to explain. How, okay, how a distillate and a residue can be obtained from fractional distillation or by the method of fractional distillation. So now, if you consider the following boiling point composition diagram of liquid mixture A and B, here we have a boiling point of pure A, which is lower than the boiling point of pure B, simply telling you that in the vapor pressure composition diagram, the vapor pressure of pure A was higher than that of B. So now, this is what we obtain, and this diagram is what exactly we looked at in the previous video, but we want to see the processes that take place when fractional distillation is taking place. So now, we shall begin by having our liquid mixture of composition C1. So when a liquid mixture of composition C1 is heated, of course, since we are looking at mole fraction of B, it means that we are dealing with a liquid mixture of composition C1 of B. So I'm going to outline the steps here. Let me first explain it. When a liquid mixture of composition C1 of B is heated, it will boil at a temperature T1, producing vapor V1, which is richer in B because we produce the vapor richer in the one whose composition has been considered. So it is going to boil at temperature T1, producing vapor V1. Don't forget that this is the vapor phase. And don't forget that this is the liquid phase. So it produces vapor V1, which is richer in B. Then condensation of this vapor V1 will produce a liquid of composition C2, which has the similar composition as that of V1. Get me properly. When we consider a composition, a liquid mixture of composition C1 of B, when we heat it, it will boil at T1, producing V1, vapor V1. When this vapor V1 is richer in B, when this vapor V1 is condensed, because when vapor is condensed, they produce liquids. When this vapor V1 is condensed, it will produce a liquid mixture of composition C2, but of the same composition as V1. Now, progressive heating and condensation will result into obtaining the azeotrope. Okay, it results into obtaining the azeotrope as a distillate, while liquid A will remain a residue. To remind you, we say that an azeotrope is a liquid mixture which at fixed pressure boils at a constant temperature to give a vapor of the same composition as that of the liquid. So we shall get an azeotrope XB at this point. Shall get an azeotrope of XB of B, of composition XB of B. So it is one which we obtain as a distillate, while A will be a residue, will be obtained as a residue. Now, when a liquid mixture of composition C4 is heated, when a liquid mixture of composition C4 is heated, it will boil at a temperature T3, producing vapor V2, which is richer now this time, which is richer in air, in air. Condensing this vapor will produce a liquid of composition C3, which is similar to that of vapor V2. And now progressive heating and condensation will result into obtaining azeotropic mixture. In all cases, we produce an azeotropic mixture as a distillate, while now B would be obtained as a residue. All right. I think I need to redraw this well here. We have C4. I need to redraw well here. This is C4. Oh, some small mistake. Let's collect it about these curves of ours. Let's collect it very well. Let's collect it very well and then we see. Let's collect it very well and then we see. Okay, so now we are saying that if I consider let me consider composition C4, which will boil at T3, producing vapor V2, which when condensed will produce a liquid mixture of composition C3. That is that. This is not there. So members, let me take you back. We are saying that when a liquid mixture of composition C1 of B is heated, it boils at temperature T1, producing vapor V1, which is richer in B. Condensing this vapor will produce a liquid mixture of composition C2, okay, which is similar to that of vapor V1. The composition of C2 is similar to that of the vapor V1, okay? Now, progressive heating and condensation will result in obtaining an azeotrope mixture, an azeotropic mixture as a distillate, while A as a residue. Now, another thing is coming to this side now. When we heat a liquid mixture of composition C4 of B, it will boil at temperature T3, producing vapor of composition V2, now this time which is richer in air. Okay, then condensation of this vapor will produce a liquid mixture C3, all right, which is similar to that of the vapor V2. The composition of this is similar to that of the vapor V2, all right? Now, by heating this mixture, it will boil at temperature T4, producing some vapor V3 continuously. The process can continue like that. Now, progressive heating and condensation will result into obtaining an azeotrope mixture as the distillate, while liquid B will be obtained as a residue. Now, let me outline those procedures on a separate page or on a separate side. Let me write these procedures here. when a liquid mixture of composition C1 of B is heated, it boils at a temperature T1 degrees Celsius, producing a vapor V1, which is richer in B. You refer to the diagram. That is the first step. Second step, when this vapor is condensed, it produces a liquid of composition C2 which is similar to that of vapor V1. Progressive heating and condensation results into obtaining the isotope as a distillate and liquid A remains as the residue. Then still we can say when a liquid of composition, when a liquid mixture of composition C4 of B is heated, it boils at a temperature T3 degrees Celsius, producing a vapor V2, which is richer in A. Condensation of this vapor produces a liquid of composition C3, which is similar to that of vapor V2. Progressive heating and condensation results into obtaining the azeotrope or the azeotropic mixture as the distillate while liquid B is collected as the residue. So in a positive deviation, we collect an azeotropic mixture as a distillate while we collect the other components as residues, depending on where you are starting from, or depending on how you are carrying out, depending on how you're carrying out your distillation. Okay. Now, from here, we are going to look at those examples of liquid mixtures that deviate positively from ideal behavior. Then I give you 2 guiding questions to do. So, let's look at, now this is the general presentation, but we are going to look at a general question. Then maybe that general question can give us limelight. But before that, let me look at the examples of the liquid mixtures which deviate positively from ideal behavior. Examples of those liquid mixtures include water and ethanol. We have benzene and ethanol. We have cyclohexane and methanol. We have carbon disulfide and ethanol. We have tetrachloromethane and ethanol. And etc. So these are the examples we can outline of those liquid mixtures that deviate positively from Raoult's law. Okay. Now, let me put here some of the examples, but in form of exercise, because they will need you to plot and then see. So let's do these guiding questions as viewers. You're going to use the general ideas I've put and maybe try doing these general examples. So they are in terms of examples, but try your best and see. Examples number 1, Roman 1, state Raoult's law. And mention its limitations. 2, explain why what is meant. Explain what is meant by an ideal solution. 3, explain why some liquid mixtures do not obey Raoult's law. Then B, the vapor pressure of a solution containing 1 mole of A and 4 moles of B is 0.75 atmospheres at 25 degrees Celsius. Roman 1, calculate the vapor pressure of the liquid mixture assuming it was ideal. 2, state how the mixture deviates from Raoult's law. Explain your answer. Explain your answer. 3, calculate the composition of the vapor above the liquid mixture assuming it was ideal, or assuming it is ideal. 4, let me call it part C. Sketch a labeled boiling point composition diagram for a liquid mixture of A and B. Of A and B. That is our question 1. Question 2. The table below shows the boiling points and mole fractions of methanol in mixtures of methanol and cyclohexane in liquid and vapor phase. Boiling point of pure methanol is 65 degrees Celsius, while that of pure cyclohexane is 81 degrees Celsius. The bracket is supposed to be closed here. So we are having boiling point of the mixture. We're going to have mole fraction of methanol in liquid mixture, and there we shall have mole fraction of methanol in the vapor phase. We have 70, 60, 55, 57, 61. 0.12, 0.31, 0.50, 0.82, 0.94, 0.27, 0.47, 0.56, 0.69, 0.83. Our part A is plot a boiling point composition diagram and label it fully. You need to know that it has got two parts. We have vapor phase up and liquid phase down. That's why you're given mole fractions in liquid phase and the one in vapor phase. So, and this is the boiling point. So we have to note them very well. Then B, explain the shape of the diagram. Then C, from your diagram, explain what happens when a mixture containing 0.2 mole fraction of cyclohexane is fractionally distilled. Is fractionally distilled. So that is the question. And from the ideas you've got, from all the ideas you've got about, from the ideas you've gotten about boiling point compression diagrams, and also about vapor pressure compression diagrams, we can be able to plot. So it's a matter of plotting boiling point, vapor pressure. All right. Then boiling point against mole fraction. So you have values of mole fraction. You will put appropriate scale from 0.1 maybe up to 0.94, and then you plot. You find you have something like this. Then you explain appropriately using the ideas we have looked at. All right. So now this is what we are specifically going to do, and that is what I want you. That is what I really want you to do. That's what I really want you to do. So, let's see. If those questions are done successfully, then we are going to know that we did some good work. We shall know that we've done some work. Okay. So okay. Yes, then let me see if I can give you an example here. Let me look at if I can give you a general example. A general example, maybe it can guide you. If we have like a mixture of chloroform that is trichloromethane, of chloroform and ethanol forms a constant boiling mixture containing 67% ethanol with boiling point 59.3 degrees Celsius. The boiling point of pure ethanol and pure chloroform. The boiling points of pure ethanol and pure chloroform are 78.3 degrees Celsius and 61.3 degrees Celsius, respectively. Let's try looking at what questions can appear on this if we are given this information. Now, the fact that the solution has a minimum boiling point at 67 degrees Celsius, that is where we are forming the azeotrope or the constant boiling mixture, then it means that it deviates positively from Raoult's law. In other words, you can see that for that particular case, you have something like this. We are having here the boiling point of pure chloroform, which is 61.3. And here you're having boiling point of pure ethanol, which is 78.3. So this is the boiling point in degrees Celsius. And since we are having percentages, let me say 0 to 100. And then composition of ethanol, let me call this one percentage composition. Of ethanol. So you realize that for this case, it will reduce, then increase. So you'll have something like this, then something like that. So at this point, that is where we are forming our azeotropic mixture. And they have told us that it is formed at 67% constant boiling mixture, 67 degrees Celsius. And it is boiling at which temperature? at 59.3. So here we are having our 59.3 degrees Celsius. Now, that is what exactly we are having. So this is the liquid phase, and this is the vapor phase. So they can ask you to explain the shape of the graph. To explain the shape of the graph, of course, everything starts from here. Since it has a minimum boiling point at 67 of ethanol, then it implies that it deviates positively. Because if they say containing 67% ethanol, then it means that here we are having ethanol, that the x-axis is having the percentage composition of ethanol. So it deviates positively from Raoult's law. And then you have to give the reason as to why it deviates positively. So if they say explain the shape of the graph, if they say explain the shape of the graph, you need to first tell me that the solution has a boiling point, a minimum boiling point at 67% of ethanol, which implies that it deviates positively from Raoult's law. Then you give me the reason as to why it deviates positively from Raoult's law. Because the force of attraction between ethanol molecules and trichloromethane molecules are weaker than the force of attraction between individual ethanol molecules and those ones of tetrachloromethane. This increases the tendency of molecules to escape from the solution to vapor phase. All right. Actually, that is what exactly we looked at. So we say that in that case, when the force of attraction between the force of attraction of the solution are weaker than those between pure and separate components of ethanol and tetrachloromethane, it implies that heat is absorbed as weaker intermolecular forces are formed in the liquid mixture, and escaping tendency of the molecules into the vapor phase increases, resulting into a higher vapor pressure. In other words, the total vapor pressure becomes above than predicted. So the solution has a maximum boiling point and a minimum vapor pressure. I beg your pardon. So we are saying that the tendency of molecules to escape from the vapor increases. Therefore, the total vapor pressure above the liquids is greater than that expected of Raoult's law of an ideal solution. So the main point is telling us that it deviates from Raoult's law, having the minimum boiling point at 67% of ethanol. Then you tell us why it deviates from Raoult's law, and that was the introduction of our previous video telling us how substances deviate from Raoult's law. But in the previous video, I was using A and B, but now I'm using ethanol and tetrachloro, or rather, and chloroform. So you have to use the aspects of ethanol and chloroform very well. Then maybe they can also ask you to explain the changes that take place when a solution containing like 90% of ethanol is distilled. 90% of ethanol is distilled. So you have to come and look out for 90% of ethanol, maybe here. If you're distilling 90% of ethanol, it means that it is going to boil at temperature T1, producing vapor V1. You condense that vapor, maybe obtain a certain liquid L1, okay, which has the same composition as that of the vapor. When this L1 is also boiled, you are going to find out that it is going to boil at temperature T2. This L1 will boil at temperature T2, producing vapor V2, which one condensed will produce liquid L2. So the whole process would be, if one is writing, let me try dictating what you would expect. When a solution containing 90% of ethanol is heated, it boils at a temperature T1 degrees Celsius, form a vapor of composition V1, which vapor will contain a lower percentage of ethanol than the original solution, because it is still the 90, and now you are going this side, you are going to obtain a vapor of lower composition of ethanol than the original. Original is 90, but now you are getting vapor V1, which will have low composition of ethanol than the original. Now, when this vapor is condensed, it is going to form a liquid L1, but of the same composition as the vapor V1. Okay, but still will contain a lower percentage of ethanol. Now, when this liquid L1 is heated, it will boil at a temperature T2, producing vapor V2, all right, still containing lower percentage of ethanol. When this vapor is condensed, it is going to produce liquid L2 of the same composition as the vapor, but still of a lower percentage of ethanol. Now, repeated vaporization and condensation will yield an azeotropic mixture as a distillate and pure ethanol as a residue. Why? That substance or that component whose composition is reducing is what we obtain as a residue. But an azeotrope is obtained as a distillate. So you heat 90%, it will boil at T1, producing V1. Which when that V1 will have low composition of ethanol, which when condensed will produce liquid L1 of the same composition as V1, but still of the same lower composition of ethanol. When this L1 is heated, it will boil at T2, producing vapor V2, which when condensed will produce liquid L2 of the same composition as V2, but of the lower composition of ethanol. So when the process is continuously repeated, continuous heating and condensation will yield an azeotrope, one azeotropic mixture as a distillate and ethanol as a residue. What if they say 30% of ethanol is distilled? If you are distilling 30% of ethanol, now we'll come and look for 30% of ethanol. You come and look for 30% of ethanol, maybe here. So that ethanol, 30% of ethanol, it will be heated. It will boil at temperature T, maybe Tx, producing vapor V1, but of a higher composition of ethanol now, because it is going to increase. So when it's condensed, it's going to produce maybe liquid LT or LX of a higher composition of ethanol. Now, when that liquid is also heated, it is going to boil at a certain temperature to give a certain vapor. So the process will continuously repeat. Still, you are going to produce an azeotropic mixture as a distillate and pure ethanol as a residue. So one would say, when a solution containing 30%, in case they said 30%, when a mixture containing 30% of ethanol is heated, it boils at temperature T1, rather Tx, I've used Tx, to form a vapor of composition V1 containing a higher percentage of ethanol than the original, because you can see the original was 30, but now we are here. Condensing this will form a liquid, maybe LX, of the same composition, still richer in ethanol. Repeated vaporization and condensation will yield an azeotropic mixture as a distillate and pure ethanol as a residue. Okay, so we have seen that for positive deviation, we yield an azeotropic mixture as a distillate, and we also yield the component as a residue. So a distillate is an azeotropic mixture. Then the other component is a residue. So we are going to look at negative deviation in our coming video. Thank you for listening.